This section of the lesson will focus on calculating the various limiting masses for takeoff. Class A aeroplanes have data presented to the pilot in a different way than smaller Class B aeroplanes. Whereas Class B aeroplane data for takeoff would show what length of runway would be used for any given mass, Class A aeroplane data shows what maximum mass could be taken for any given runway length. This makes more sense, since Class A aeroplanes are used commercially, and the interest of the airlines is to carry the maximum payload possible for the flight. Therefore, most performance graphs or tables will give a mass as their outcome. The first of these performance masses is the field limit brake-release mass. Before we work through the graph, it is important to understand what this mass means. The field limit brake-release mass is the maximum mass that will allow the airplane to meet its field length requirements at the airfield concerned. Therefore, to be heavier than the field limit mass would mean that either the one engine inoperative or the all-engine inoperative takeoff run, takeoff distance, or accelerate stop distance exceeds the available distances at the airfield. If you remember, airfields can have different lengths of takeoff run, takeoff distance, and accelerate stop distance, as shown. Therefore, there should be many mass graphs. There should be a mass graph for ensuring that the mass is such that the takeoff run required is within the takeoff run available, that the takeoff distance required is within the takeoff distance available, and lastly another mass to ensure the aeroplane's accelerate stop distance required is within the accelerate stop distance available. However, there is only one graph, and only one assumed available distance to calculate the field limit mass. The reason is for simplicity. The graph assumes that the takeoff run, the takeoff distance, and the accelerate stop distance available are the same length, even though the takeoff distance available and accelerate stop distance available may be longer. Therefore, no stopways or clearways are accounted for. When the takeoff distance available and the accelerate stop distance available are the same, the field is described as being balanced. In this case, the balanced field length also happens to be the same length as the takeoff run available, because there are no stopways or clearways assumed. To use the graph, make sure you only enter the takeoff run available as the length of field available. Let us work through an example. Enter the bottom of the graph with the field length available, which for the purpose of this graph must always be the takeoff run available. In our example, let us say the Tora is 8,000 feet. Move up vertically from this point until the runway reference line, shown here. Now travel either up or down the runway slope lines. We'll use a 2% upslope on our runway, so travel up and left using the guideline until 2% upslope is reached. From this point, move up vertically until the next reference line, which is for the wind. For tailwinds, travel down and left, paralleling the guidelines, but for headwinds, travel up and right, paralleling the guidelines. In our example, we'll assume a 20-knot headwind. Remember that this is not necessary to factor by 50%. The graph already does this for you. After correcting for the wind, move vertically to the next reference line, which is for the flap setting. If the flap setting were 5 degrees, then keep moving vertically upwards. But in our example, we'll assume 15 degrees. Therefore, travel up and right, paralleling the guidelines until 15 degrees flap. Then move vertically upwards through the graph, leaving a line so we can return to it. Next, we will need to account for temperature and airport pressure altitude. On the left-hand side of the main graph, we'll use an example of 25 degrees Celsius at an airport pressure altitude of 2,000 feet. So, travel up vertically from 25 degrees Celsius until 2,000 feet. Then move horizontally to the right until the reference line, shown here. Now we need to find our line that we drew from earlier. Notice it is to the right of the reference line. Therefore, travel up and right, using the guideline, until you reach the line from earlier. Then, move horizontally to the right and read off the field length limit mass. In our example, the field length limit mass is 59,200 kilograms. However, this mass may need to be corrected. Examine some of the information in the bottom left-hand side of the graph. It states that the graph is based upon the air conditioning packs being on automatic. Therefore, if these are off, there will be more thrust available and the field limit mass may be increased by 550 kilograms. Beneath this is the correction for anti-ice. If the engine anti-ice is on, then the allowable mass has to be decreased by 350 kilograms. Lastly, there is a correction for the power management control. The graph assumes that the power management control is on. Therefore, this is the correction box for when the power management control system is off. The field limit mass is not the only mass that must be considered in the takeoff. There are several more. The next mass to consider is the climb limit brake release mass. The graph for calculating this mass is figure 4.5, which is on page 11 of section 4 in cap 698. The climb limit mass is sometimes referred to as the weight altitude limit or mass altitude temperature limits, abbreviated to watt or MAT limit. Before we work through the climb limit mass graph, let's try and understand what this mass means. The climb limit mass is the maximum mass that will enable the aeroplane to achieve a certain minimum climb performance. This minimum climb performance is the most severe of the climb gradient requirements. The most severe of these is 2.4%, which will be covered later in the next lesson. In other words, if the mass of the aeroplane were greater than the climb limit mass, then the aeroplane may still be able to climb, but it will not achieve the minimum air gradients that the authorities have laid down. Try to remember that these gradients are air gradients and are therefore unaffected by wind. In order to help you calculate the climb limit mass, let's work through an example. Start with the temperature at the bottom of the graph. In this case, we'll assume 25 degrees Celsius. Move vertically upwards towards the airfield pressure altitude, which in our example will be 2,000 feet. Then move horizontally to the left and stop at the reference line, shown here. Depending on the flap setting selected for takeoff, will determine where we go next. If 5 degrees flaps were selected for takeoff, then just travel straight across. Whereas if 15 degrees flaps were selected, as in our example, travel down using the guidelines to the edge of the graph and read off the climb limit brake release mass. In our example, the climb limit mass is 56,000 kilograms. However, as with most other graphs, check that there aren't any corrections to be made. Looking at the bottom of the graph, there is a list of corrections. This is the correction if the air conditioning packs are off. This is the correction if engine anti-ice is on. And lastly, the table at the bottom is for corrections with the power management control system being off. The next mass to consider is the tire speed limit mass. The reason for a tire speed limit is simply because naturally there will be resistance between the wheel and the runway. As the wheel rotates, this resistance generates heat, as shown by these thermal images of an aeroplane just after takeoff. Notice the white areas that are signifying the hottest temperatures. The greater the wheel speed, and/or the greater the load on the wheels, the greater the heat generated. Too much heat will not only disintegrate the tire, but it may also expand the air within the tire and may overpressurize it. This is dangerous and may result in a tire blowout, although there are fusible plugs in modern tires to try and help prevent this. As you can now understand, there is a maximum ground speed and maximum mass that the wheels are subject to. The maximum ground speed that the tyre will experience will be at VLOF, and as a result, tyre speed limits are designed to be slightly faster than VLOF. For most medium-range jet aircraft, the maximum tyre speed is set at about 195 knots, which is 225 miles per hour. Let's work through an example on how to calculate the maximum tyre speed limit mass. The graph for this is figure 4.6 on page 13 of section 4 in CAP 698. Previously, we used an example temperature of 25 degrees at an airport pressure altitude of 2,000 feet. So move up vertically from 25 degrees until 2,000 feet. Then move horizontally to the left to read off the tyre speed limit mass, which in our example is 82,400 kilograms. This mass is based upon flaps set at 5 degrees. So lastly, ensure there are no corrections to be made to this mass. These corrections are listed in two tables at the bottom of the graph, shown here. The first table makes corrections to the tyre speed limit mass for 15 degrees flaps, for lower tyre speed ratings, and for headwinds and tailwinds. In our example, we will assume 15 degrees flaps, which increases the tyre speed limit by 6,600 kilograms. We have also assumed a 20-knot headwind, and therefore by correcting for 400 kilograms per 1 knot, means that the tyre speed limit mass will increase by 8,000 kilograms. With the corrections applied, this makes the tyre speed limit mass to be a total of 97,000 kilograms. The very last table is the correction factor for the power management control system being off, since the graph assumes that it's on automatic. One of the last masses to consider is the obstacle limit mass. The obstacle limit mass is the maximum mass, in the event of engine failure, that the aeroplane can be at in order to achieve the minimum clearance over an obstacle in the takeoff flight path. If the mass of the aeroplane were greater than the obstacle limit mass, then there is no guarantee that the aeroplane will clear the obstacle by the minimum clearance level. This may seem to be a limiting factor, but of course, if the aeroplane cannot clear the obstacle vertically, it can of course go around the obstacle. The method of calculating the horizontal clearance will be discussed in the next lesson. Before we work through the graph, there is some preamble about the obstacle limit mass graph on page 35 of section 4 in CAP 698. It states that the graph is a rapid means of obstacle clearance calculation when there is no detailed information available. It also states the graph is not valid for air conditioning packs being off or for takeoffs using the improved climb technique. Let's now use an example to work through the graph. There are two graphs, one for 5 degrees flap and the other for 15 degrees flap. In the previous examples, we used 15 degrees flap. Let us say that the obstacle height is 200 feet and the obstacle is 18,000 feet away from the brake release point. Enter the graph with 200 feet and move horizontally to the right until you hit the 18,000 feet line. Then, move straight upwards and hold at the reference line for outside air temperature. The outside air temperature in our example is 25 degrees Celsius. Therefore, from the reference line, move down using the guidelines until 25 degrees. Then move vertically upwards until the next reference line, which is for the airport pressure altitude. In our example, this is 2,000 feet. From the reference line, travel up and left, using the guideline until you reach 2,000 feet. Then move vertically upwards until the next reference line, which is for wind. Move down and left for tailwinds, or move up and right for headwinds. In our example, we have 20 knots of headwind. Therefore, move up and right until 20 knots, and then move straight up to read off the obstacle limit mass, which, in our example, is 54,300 kilograms. Lastly, ensure there are no corrections to be made. For example, if the power management control system was off, which in our case it isn't.